Okay, the last calculus practice question for today is the related rates question. It's kind of a classic one about a ladder sliding down a wall. Let's see if we can make a diagram of this situation. So here's our 10-foot ladder, and it's slowly sliding down the wall like this. And as it slides, its horizontal distance to the corner change and its vertical distance to the corner change until it slaps against the ground, and now it's flat on the ground like that. So notice something interesting. If I play that at a constant speed, they said that the horizontal distance is traveling at a constant speed. So that one's increasing at a constant rate. Notice how the vertical distance is decreasing at a non-constant rate. It starts off slow, but then it gets really fast as it hits the ground. And in fact, that's why it makes that smack when it hits the ground. Yeah, see how it like starts off really slow when it's at 9.9, but then it gets faster and faster and faster and faster, and then really fast when it gets to the bottom. Let's see if we can capture that in an equation and relate how fast the x distance is changing and how fast the y distance is changing. So first of all, what's the fundamental relationship between these three values, the y distance, the x distance, and the length of the ladder, 10? Well, you can see that they always form a right triangle. So they always should satisfy the Pythagorean theorem. So the Pythagorean theorem is going to be the starting equation for us to sort of get a grip here. So applied to our ladder, the Pythagorean theorem tells us that that x distance squared plus that y distance squared equals 10 squared. So with just that equation alone, we're able to relate the current x distance and the current y distance to each other. So for example, if they wanted to know, like, when the x distance is 5, what's the y distance? We could figure that out just with this equation. But they're asking about the rates of change of those things. So we can't just use this equation. We have to kind of upgrade this equation with a little bit of calculus. We will use implicit differentiation on this thing for the next step. So just to clarify, that is our equation for part A, but now we need to take the time derivative of both sides in order to figure out part B. So if we take the time derivative of both sides, well, that's just using implicit differentiation. So x squared becomes 2x, but because x is a function of time, we then have to multiply by the derivative of x with respect to time. And then the same thing happens for y. This is 2y times the derivative of y with respect to time. And then the derivative of 100 with respect to time is 0. And that corresponds to the fact that the length of the ladder is not changing over time. So there's nothing happening on that side. Okay, so now we need to figure out how fast was the ladder sliding down the wall. In other words, they're asking for dy dt when x was 6. So we'll fill in 6 for x. dx dt, they said, was always 2, right? They said that it's sliding away from the wall at a constant rate of 2. So dx dt is simply 2. But then we're still left with two unknowns here. We got y and dy dt. Let's go back to our diagram for a second. So we're specifically interested in this moment here when x is equal to 6. Whoops, if I can get it just right. When x is equal to 6. Now my diagram kind of spills the beans that means y has to be 8. Now why does y have to be 8? Because of the Pythagorean theorem, right? We know that that's the way that those are related. If I take this equation, the Pythagorean theorem equation that we started with, and I replace x with 6, then I can solve that equation and figure out that y has to be 8. So at that moment, when x is 6, we know that y has to be 8. So, okay, we can fill in that y value with 8, and that means now dy dt is the only remaining variable in our equation, so we can solve it for that. That's going to be 24 plus 16 dy dt equals 0. And then if we solve that, we find out that dy dt is negative 1.5. So at the moment when the ladder is 6 feet away from the wall horizontally, and it's increasing that distance at 2 feet per second, Well, then the vertical distance is currently at 8 feet, and it's decreasing at a rate of 1.5 feet per second. So not as fast as it's going sideways. It's going sideways faster than it's coming down. But then once we pass a certain spot, that flips, right? Now the vertical distance is increasing very quickly over here. But it's not asking us about that spot. It's just asking us about when it is equal to 6. Okay. Okay, so finally part C is asking, is the top of the ladder moving faster or is the base of the ladder moving faster? Well, the base of the ladder is moving at a constant speed of 2 feet per second, and we just calculated, whoops, I made a mistake here, that this was negative 1.5. The top of the ladder was moving down the wall at a rate of negative 1.5. So it is at that moment moving slower than the base of the ladder. However, as we have seen in the diagram, it is going to speed up. So later it's going to be moving faster. But right at that moment, it's still moving slower than the base of the wall. So there you have it. Best of luck to you on your calculus exam.